Hey, hello. Yeah, I'm Brian. And again, this is a paper about hidden role games, and it's joint work with Luca here. Gabriele, where are you? You're here. Nicola, who is not here, I believe, and Tuomas, who is here. Great. Okay. So, what are hidden role games? This is a class of games also known as social deduction games. Probably most of you in the room have played at least one of these at some point. These are adversarial games in which there is one team, commonly known as the good team, that does not know who their teammates are, and one team, commonly known as the bad team, who do know who their teammates are. And in these games, there's an emphasis on communication. So players are usually free to talk to each other, free to try to establish trust and coordinate actions. But of course, if you're a good player and you send a message to somebody, you don't actually know whether you're talking to a good player, right? It's possible that the player that you're talking to is actually bad. And of course, there are many examples: Werewolf, Mafia, Avalon, Among Us. If you play this is a popular game from the past couple of years, and practical application for distributed systems, network security, federated learning, so on and so forth. Okay, so what do we do? Well, to our knowledge, we are the first to study this class of games from a formal game theoretic point of view. So let's trying to understand, first of all, what are reasonable solution concepts for these games, and how do we compute equilibria for how do we compute these solution concepts? And as an application, we look at the popular game of Avalon, and we actually exactly solved 5 and 6 player variants of Avalon. And of course, I'll get to know. I'll say more about how we do this when I get there. But first, I want to spend some time talking about solution concepts. And it turns out to be not very easy to define what the right solution concept in this is for hidden role games. Luca and Tuomas knows, Gabriele knows very well. We spent long meetings in our offices trying to figure out what the right solution concept would be for this class of games. Okay, so you might ask, well, can we just use some solution concepts that we might all be familiar with? Like, can we just use Nash equilibrium? I mean, it's the most basic notion of equilibrium, right? What happens if we just use Nash? Nash equilibrium doesn't capture team coordination very well. So for example, if I have a game where there's no adversary, which is a special case, then I want my solution concept to encode the optimal joint strategy for the team, which Nash equilibrium obviously does not, right? Okay, so there are notions of equilibria that do encode this team coordination phenomenon, perhaps most notably the team correlated equilibrium. So when the teams are common knowledge, perhaps this is the most natural concept. It is the concept in which the teams are allowed to flip random coins beforehand, but once the game starts, maybe they're not allowed to talk anymore. But here in hidden role games, what would it mean to correlate with a teammate that you don't even know? That's a little bit problematic. So all of this basically means we need some new solution concepts. Okay, so what do we do? The first step is that we define this game that we call the split personality game. So we take a hidden role game in which each player, could be either on the good team or bad team, and we split each player into 2 players, one of which will take over for the player when they're on the good team, and one of which will take over for the player when they're on the bad team. So now we have a game with twice as many players, which is a true team game, right? We have n players on the good team and n players on the bad team. Right? And we will define a hidden role equilibrium to be an uncorrelated strategy, to be a team uncorrelated equilibrium of the split personality game, also known as an optimal strategy for the good team to commit to. And you might ask, okay, I'm talking about commitment. Why am I talking about commitment in the zero-sum game? Shouldn't like Minimax theorem or something like this hold? Well, no. It turns out that there is an inherent reason why this notion of equilibrium is and kind of must be asymmetric. And in fact, intuitively, if I have a hidden role game where the minimax theorem does hold, in order that is, if the bad team could commit just as well at first and without changing the value of the game, then you can show that essentially the good team can cause the whole team to be revealed by basically picking a long random string that the bad team will never say and getting all the good players to publicly announce that string. And now all the teams are public, and you've completely ruined the point of having a hidden role game in the first place. So that's not great. So this is why we insist on having this asymmetric notion where the good team commits first. And of course, the fact that the good team is committing first here is sort of inherent to the fact that the good team for us is the team that doesn't know who the teammates are, right? We have this inherent asymmetry in the definition of the game, and therefore, and also an inherent asymmetry in who commits. Question.
Just a super quick question about your use of the word commitment. Does that mean that they actually commit to those actions, or do they have freedom to revise the actions later?
They commit to a mixed strategy.
Okay.
So each player is going to publicly announce, well, this is what I'm going to do if I'm. Okay. Let me go through an example, a very simple example, maybe that may be clarifying some weirdness that pops up with this class of games. Okay, I'm going to have 3 players, 2 of which are good, and 2 of which will be on the good team, and 1 of which will be on the bad team. So I will have 3 cards, 2 of them say good, 1 of them say bad, and these cards are going to be placed face down and randomly distributed to the players. Now the players can see what's on their cards, but this is private information. The other players don't know this. Then they'll have some sort of conversation, and then there will be a simultaneous vote. And the rules of this example game are as follows. If there is a majority vote, if somebody is elected, then whoever is elected wins on behalf of the team. If a good player is elected, then good wins. If the bad player is elected, then bad wins. Okay, so in this case, in the previous case, good would win. In the previous case, good would win. And if 2 players elect the bad player, then bad wins. If everybody votes for themselves, or otherwise, if there's no majority vote, bad wins automatically. Okay, so in some sense, this game is kind of trivial, in the sense that there is a perfect symmetry between the players, and essentially, if you're a bad player, you can perfectly imitate what a good player would do, and then the good team, and then the good team basically can't gain any information. So the value of this game is anybody?
2/3.
2/3. Good. Okay. So yeah, the good team can't learn anything. So the best thing to do is just select somebody arbitrary and you get 2/3. Okay. I'm going to make one small change, which doesn't seem to do anything, but I'm going to claim will do something, which is I'm going to make a mark on one of the good cards so that now they are distinguishable. So now we have good prime and bad. I claim that this changes the value of the game. And I am going to stop for about 20 seconds to let you guys think about this before I reveal what the solution is. But yeah, good can win deterministically.
Everyone always votes for like, oh, actually, no, it's not full deterministic, is it?
Good can win deterministically now.
So maybe one of these good or good prime always vote to himself, the other one.
It involves communication.
Oh. Everyone announces their type.
Everyone announces their type. Yep. So just to be concrete about this, one player is going to be good, one player is going to be good prime. The good players are going to announce their type, which leaves the bad player in quite the dilemma. In particular, if the bad player claims to be good, then you can elect good prime. If the bad player claims to be good prime, you can elect good. If the bad player claims neither, then of course they're immediately outed as bad and the game is over. So yeah, what has happened here, right? Like I've changed something that seemed to have no effect on the game and had an effect on the game. What's happened here is that I've implicitly allowed the good players to correlate with each other. Like this is what happens as a result of the fact that we're prohibiting correlation between the players. The distinguishability of the 2 good cards is a bit of correlation that the 2 good players can use to increase their utility. Okay. So the distinguishable cards leads us to this sort of implicit correlation effect. Okay, so now I'm going to talk about algorithms for solving this family of games. Okay, I'm going to make a couple of assumptions, which in this family of games that when they're played in practice are basically always true. The bad team is a minority if it has strictly fewer players than good. Most games that you would play, for example, Avalon definitely has this property. And the bad team is coordinated. This is a bit of a stronger assumption. I'm going to say the bad team is coordinated if informally the team acts as if it's being controlled by a central controller. The team acts as if there's one central controller that is basically observing all the private information of all the bad players and controlling all of the actions. Whether this is a valid assumption depends on, for example, the size of the bad team. So if the bad team has only 1 player, then this is obvious. If the bad team has multiple players, but they don't really have any meaningful private information to speak of, then this is still true. Because, if the bad teams have the same information, then you could basically coordinate anyway. And our main positive result, is that under these seemingly reasonable assumptions, private communication is allowed, a team bad is a minority, and team bad is coordinated. We have an efficient algorithm. And with this private communication assumption, I'm going to argue that private communication, although perhaps a priori unreasonable, is actually quite reasonable, at least if you're playing with computers, because because if I have public communication channels, I can just do pairwise public key encryption and develop private channels that way. And it turns out that this is essentially the only positive results that you can write down. If you break any of the assumptions, then things go wrong. I guess there is one ingredient here that is still an open question for us, which is what happens if I assume everything except the minority thing? What happens if I assume that private communication is allowed, but that bad team is coordinated, but the bad team can be a majority? Can I still get something efficient in that case? We don't know. Okay. I am going to give an overview of how this positive result is proven because it's kind of interesting. Used a lot of ideas from cryptography, some of which I've already sort of alluded to. The first idea is, of course, if I don't allow private communication, I can construct it by public key cryptography. Okay, so first, the first idea is this: suppose that there is a good player, who we call the mediator, who is always on the good team, so guaranteed to be on the good team, and everybody knows this. But the mediator doesn't really do anything else in the game. The mediator doesn't really take actions. The only power the mediator has is that everybody knows that they're good, and the mediator can say stuff. So what should you do with that mediator? I kind of have it on the slide here. You should essentially use the mediator as a coordination device. So all the good players should tell their true information to the mediator. The mediator should accept all of this information and then attempt to coordinate the actions of everybody on the good team. Well, of course, if you're a bad player, you should probably lie to this mediator and you could. And you can try to disclose some private information that a good player might have. And the mediator might recommend you an action as well. And of course, you're free to disobey that action. Bad players are free to do whatever they want. But good players will always tell the true information and will always obey the action recommendations. Bad players can do whatever they want. And the first main idea is that if we allow private communication, if we allow this setup to work, then when bad is coordinated, what we have is a two-player zero-sum game. It's a two-player zero-sum game between the mediator and the bad coordinator. And so since this is a two-player zero-sum game, you can toss it to any old two-player zero-sum solving algorithm and solve this sort of. So this already has an interesting implication, which might be surprising, certainly was kind of a surprise to us, which is that the game values of these games are rational. I don't know of another proof of this, weirdly enough. The only proof I know of this is by going through this machinery. And the second main idea is this. Okay, suppose we don't have this mediator. Well, in most games, you don't have this. So what do? Well, we use cryptography to simulate one. Multi-party computation is a thing. And as long as the good team is a majority, you can always simulate a mediator like this with multi-party computation. And assuming the good team is a majority, this basically cannot be broken. And of course, okay, you'll lose some epsilons here having to do with the probability of breaking the multi-party computation, but that's fine up to these small epsilons. You can basically simulate perfectly what would happen with the mediator, and therefore you get the same value. Okay, so I guess I'm going through this rather quickly. So if you guys have any questions, please let me know. Yes.
A very stupid one. What does the implies that game values of hidden value games are rational actually even mean? What does it mean to be rationalizable in this context?
No, rational. It is a rational number.
Oh, it's a rational number. Got it. Oh, okay. I was like, okay.
Yeah, this is not obvious a priori. Like I define this like team game. It's some sort of like weird max-min problem, which is not even really linear in some sense. It's possible that these values are irrational. Yes.
If it's a rational number, but only up to a delta, how is that not the same as saying that it's not necessarily a rational number?
What do you mean by up to a delta?
So you said there's some chance of breaking the.
Oh yeah. Here, I can take this chance to be arbitrarily small by allowing more and more communication. So like if in the game where I allow arbitrarily unbounded communication, the max team can commit a priori to an arbitrarily high security multi-party computation algorithm and get arbitrarily close to this game value. So we're going to call that the game value. If you can get arbitrarily close to it. For every epsilon, I can get game value minus epsilon. Any other questions? Okay, I guess I'll move on. And yeah, as I alluded to at the beginning, Our application is that we exactly solve 5 and 6 player resistance Avalon. And I'm going to spend a little bit of time discussing some implications of this. Okay, so with Avalon with less than 7 players, our analysis applies. Why less than 7? Because with 6 or fewer players, there are only 2 bad players, so they know each other's roles, so there's no private information among the bad team. So we can assume the bad team is coordinated. With 7-player Avalon, if there is ever the case that, you know, there are multiple bad roles, like for example, I might have 3 bad cards, one of which has something different on it because that's a special role, then the bad team doesn't know who has, then the 2 other bad players might not know who has that special bad card. And then full analysis breaks because this team is no longer coordinated. And before I get into the table, I just want to say that this was a massive computational effort involving a lot of simplifications that more or less amount to removal of dominated strategies and simplification of the game to get it down into a form that can be solved with a linear program. Exactly, yes.
Can you solve this for 7 players without Morgana and Mordred?
Without, sorry?
Without Morgana and Mordred.
So it was known before us by Cristiano that with no special roles, every variant of Avalon is a perfect win for the good team with Merlin.
I haven't played Avalon in a while, but like, are you saying that you're solving a round of voting or the entire?
We are solving the entire game.
You're
We're solving the entire game.
Okay.
So with no special roles, these four values on top were known to a blog post of Cristiano in 2018, which is that with Merlin, these 2 values are perfect, right? Because if you know how Avalon works, the bad team has a probability of guessing Merlin at the end of the game that cannot be prevented. And so modulo that value, you win every time. So you win every time without revealing any information about Merlin. And our contribution here experimentally is that we determine these values. With Merlin and Mordred, for example, the value is exactly 731 out of 1782. Don't ask me what the strategy is. You might ask, what the heck is Merlin and 2 Mordrads doing here? Isn't this a Merlin that knows nothing? Well, no, not quite. Because this is the implicit correlation thing. The good cards are now distinguishable. If you were to have a Merlin card that was indistinguishable from the other good cards, you would expect the value to be 0.2, right? This is 0.3 multiplied by 2/3 probability of guessing the right Merlin. But this is greater than 0.2, and the only reason this is greater than 0.2 is because of this sort of implicit correlation effect that I was mentioning. And yeah, this was too large for us to solve. But okay, we have the other ones. And yeah, 7 players, you can probably solve if you make the assumption that the bad team is coordinated. But that's probably too strong of an assumption by a little bit because again, you know, the bad team doesn't necessarily know who has the special card. Yes.
Okay, I think I'm just confused here. So you said that with no special roles, the good team always wins deterministically.
The good team, no. With only Merlin, the good team wins deterministically.
With only
Merlin. So this.
No special bad roles. Yeah. With no special bad roles.
No special bad roles. The good team wins deterministically.
Okay.
So with no special roles at all, these values are pretty bad. I think we can all, yes.
Can you lower bound the winning probability of the good team if you assume that the bad team is coordinated with 7 players or more?
Yes, that will work. Yeah, so essentially, and you might ask another question that I have gotten before with in this sort of game, is it true that all of these strategies involve not revealing any information about Merlin? No. So we have in the appendix of the paper a human readable description of what exactly the strategy is, and the bad team guesses Merlin with probability better than 1/3. So you know the information about Merlin is used in a non-trivial way there. I just want to close with some future research. So this is a new class of games for which we can reasonably define what it means to solve a game, right? So, and I think there are so many open questions. So one of which, one open question I already alluded to on a previous slide. It's, you know, is there an efficient algorithm or a hardness result for the case of coordinated and non-minority bad team? And the second question is kind of a weird one. It's if I allow only public communication, and I enforce this by saying, for example, the bad team is computationally unbounded and therefore can break all cryptography. So you really can only do public communication. It is not even clear whether a finite time algorithm exists. I don't know of a finite time algorithm, at least. And the reason why I don't know of a finite time algorithm is because I don't know how to bound how much communication you need. If you could bound the amount of communication, you can write down the game that uses that many rounds of communication, and it's a finite game and you can solve it. So I think this is the second question here is kind of very interesting for practical applications, because in practice, when you play Avalon, you probably don't want to be doing public key cryptography on the game. And okay, other messaging structures. So for example, if I allow anonymous messages, what happens? By anonymous here, I mean, let's say I allow messages where I can broadcast a message without revealing that I am the one sending the message. Then what happens? We don't model that in ours. And also, what happens when both teams are hidden? We have a little bit of discussion about this in the paper, but suffice to say, it becomes even hard to define what the right notion of equilibrium is again, because now you have to make a decision about who is the one to commit. And that's not an obvious decision, because as I alluded to before, the reason why we make this decision here is that the good team is the one to commit is because the good team is the one with the private with the hidden information. But if both sides have hidden roles, who should be the one to commit? There is no minimax theorem, so in some sense you really have to decide this somehow, and it's not clear how to do it. And that's all I have.